presentation, I will not overload it with technical details such as technical drawings, specification tables, performance tests, etc. Instead of that, I will present the most important features of our instrument and also mention the most important ingredients which are required for making high precision polarimetry with a CCD detector. So let me start with my presentation. So if I would be asked to propose a design of a simple yet efficient CCD broadband polarimeter, I would not hesitate to recommend this one. So the simplest CCD polarimeter would consist of a filter wheel, discretely rotated half or quarter wave plate, a double beam polarization analyzer, and a CCD camera placed in a focal plane of the telescope. Actually, our first CCD polarimeter built into our observatory some 20 years ago and used for more than 10 years on a remotely controlled 60 centimeter KVA telescope at La Palma has exactly this design. So with this polarimeter, if you want to measure linear polarization, you should use a half wave plate, take 4 images, the different orientation of half wave plate, separated by 22.5 degrees, and then you can compute the normalized Stokes parameters Q and U from the intensity ratios of these two orthogonally polarized stellar images recorded by the CCD. If you want to measure circular polarization, you should use more or less the same method, but with a quarter wave plate. So this polarimeter is simple, efficient, and it has a very high light throughput, negligible light losses, negligible instrumental polarization, negligible aberration introduced to the exit pupil of a telescope. And this polarization, this polarimeter layout has been used in modified forms in many existing and existed instruments. What is the main advantage of such instrument is, of course, a dual image, because you use a double beam polarization analyzer. Both orthogonally polarized images are recorded simultaneously on the same detector, and the ratio which is used to compute polarization is not affected by any changes in atmospheric transparency and C. Okay, because my talk is focused on accuracy, I will say a couple of words about the most important factors which affecting accuracy of polarization measurements. First of all, of course, these are the photon counts, signal to noise. So the accuracy depends on these two factors. So if we assume that the only source of random errors in measured polarization is the photon short noise, and the sigma of a normalized Q and U given with a simple formula. Here K is an analyzer efficiency, and N is a total number of photoelectron registered for both orthogonally polarized ordinary and extraordinary stellar images. So what does it mean? It means that this formula puts a very strict limit on the accuracy which is attainable for any given polarimeter. And practice, you may have a larger error than this one, but not smaller. That means that if one wants to have an accuracy, the sigma, the level of 0.001% or 10 to minus 5, 10 to 10 photoelectrons must be recorded per single polarimetry measurement cycle. So the polarimeter is for an Hungry technique. So if you want, for example, to reduce an error, let's say 2 times, 4 times more EDUs must be collected. Another important formula relates a signal to noise ratio in combined O and E images for the desired sigma P. So it's just taken, copied by me from the paper, published by Paylet and Ramoniello. And according to this formula, if your number of half-wave position is 4, it converts to the very simple ratio. The signal to noise is equal to 0.7 divided by sigma P. So if sigma P desired is 0.1%, the signal to noise which is required is 700 in each of dual images and each of 4 CCD exposures. I must mention that there is no widely accepted or commonly accepted definition of high accuracy. So different researchers from different research group may assume very different things when they say high precision measurements. For example, for most of AGN people, if a sigma p is, let's say, 0.1%, the error is small and the accuracy is high. But the researchers working with the Hippie polarimeter will certainly not agree with this definition, because for them, if sigma is 0.01%, the accuracy is low. So in my presentation, I will assume a definition adopted by the hippiest people. So when I say high precision, I mean accuracy at level 10 to minus 5 or better, which requires, as I already mentioned, 10 to 10 photoelectrons collected per polarization measurement cycles. So a CCD camera is probably the best detector for optical and near infrared, as you probably know. And for the faint stars, the main factor which limits the accuracy of CCD polarimetry is signal noise. Because with the faint star, you won't be able to collect 10 to 10 photoelectrons in any reasonable integration time. However, when you want to measure polarization with a high accuracy from a bright star, the early pixel saturation becomes a CCD bottleneck and the main factor limiting accuracy. The typical full well depth for the CCD cameras is something like 200,000 photoelectrons per pixel. And to avoid saturation, short exposures must be used and many thousands of images must be taken to collect this required high number of photoelectrons. Because of typical CCD image download time is somewhere between, let's say, 20, 50 seconds, the image download time, the overhead spent on download, much larger than the total exposure time. So such observations become very inefficient and cannot be used in practice. So not surprisingly, a photomultiplier tubes and avalanche photodiodes has been considered as best detectors for high precision polarimetry domain. So they have much wider dynamical range, they can tolerate much higher fluxes, and they have an instant readout. So they may be used in combination with high frequency modulators such as PIMs or FLCs. So because of that, the most of high precision polarimeter used PMT or APD detectors. So the first record breaker Planet Pole, which was the first instrument capable to measure polarization of bright stars with accuracy few parts per million used in APD, still exist in Polish 2 and Hippie polarimeters use PMT as detectors. Of course, the PMT and APDs has their own disadvantage. They're not as sensitive as CCD cameras. They are more noisy in general, and they are single cell detectors, so the polarization of a sky should be measured separately, which is not very convenient. Nevertheless, it was believed then a CCD camera is the best detector for low flux polarimetry domain, while the PMT or APD is a detector of choice for a high absolute accuracy domain. So for us, when we decided to upgrade our existing Dipole 1 with the next generation instrument, it became a challenge to make an instrument which, as we desired, should be efficient in both domain, high accuracy and low flux. But there are other factors which are affecting polarimetry. First of all, it's a telescope polarization. So it must be measured with the same or better accuracy than the polarization of your program star. And if you opt for high precision, significant fraction of observing time must be spent on observations of zero polarization standards. And the telescope focus choice is also very important because a very popular Nesmin Coude foci gives strong and variable telescope polarization. It can be in principle modeled and removed, but on practice, it's very difficult to do this with the accuracy better than 10 to minus 3. That the Cassegrain focus is the best choice for high precision polarimetry. And the focal reducer of field correcting lenses is not a good choice because they can and very often produce strong and field-dependent polarization. So straight Cassegrain with no any additional lenses. So the choice between the equatorial and alt-azimuthal mounts in principle means the choice between the constant and the variable with the zero angle telescope polarization. With azimuthal mount, the direction of telescope polarization will change as a sinusoid with the zero angle. So most of the Cassegrain type telescope have a telescope polarization in the range significantly less than 10⁻⁴. So for most applications, it can be simply rejected. But if your intention is to measure polarization of program star with accuracy 10⁻⁵ and better, you must measure this polarization and measure it with a significant level of confidence. In order to do so, you should properly select the zero polarized calibration stars. So most suitable for this purpose are stars of A, F, and J spectral types. They must be single, non-variable, no spots, no magnetic field, no strong magnetic field, no debris disk, geysers, or dust envelopes. In such case, two stars should not demonstrate any intrinsic polarization up to 10⁻⁶. However, there are several problems you may face with choosing these stars because comfortably faint for the large telescope stars are distant and can be polarized by the interstellar medium, by the interstellar dust grains, and nearby stars too bright for the large telescope, again the saturation issue, and even the nearby stars can be polarized up to 10⁻⁴ by the local interstellar medium. So even for such stars, for the stars at a distance, say, less than 50 parsecs, there may be still some residual ESM polarization component just on the top of a telescope polarization. So recently we have published a paper with the measurement of polarization of 360 nearby stars. And the picture shows the one of the picture taken from this paper. It shows a distribution of magnitude and direction of polarization over the sky for the stars at a distance less than 50 parsecs. So as one can see, local interstellar polarization tends to have a different direction as a different part of the sky. Thus, as we think the best way to get rid of this residual interstellar polarization component is to measure quite many, 15 to 20 stars at a different part of the sky and average their stocks, Q and U parameters to get the value of a telescope polarization. So by doing so, this residual ISM component should be cancelled. And we are following this approach, and with way we can measure the telescope polarization with our dipole tube with accuracy few parts per million. Okay, so when we decided to upgrade our first CCD polarimeter, we have accepted certain design requirements according to our research interest and our primary goals. First of all, we wish to have a polarimeter free of systematic error to the level of 10⁻⁶. We also wanted to have a simultaneous observation as a free passbands with the high sensitivity in the blue band, which is sensitive for the relay scattering. We wanted to have a polarimeter with a minimum light losses. It is equally important for observations of faint and also bright stars. We wanted to make an instrument which is suitable for mounting on small and large telescopes. We want it to be reliable, service space, suitable for remote observations and long continuous observing runs. We also wanted to have it simple and easy to use with the simple calibration and data reduction routines. And last but not least, we wanted to have a polarimeter which is cost efficient and easy to build. So we are a small team in Torla, just only two of us, me and Vilpo. And we wanted to make it cost efficient and simple so there's several units can be produced in a few years at low cost, so we could put this polarimeters in the different telescopes and different observatories. So Dipole 2 is just a successor to this dipole 1. So we retain the core features of first polarimeter, added the new features. And of course, the most important feature, which must be mentioned here. So we wanted to have a CCD polarimeter, equally efficient and high precision polarization measurements domain and low flux polarization measurement domain. So as I said already, it's a joint project between two institutes. One is our Finland, another is KISS, Germany. And the Dipole 2 is designed and built on Thorla Observatory by Vilpo Pirla. So you can see him on the lower photo, and the upper photo shows the joint Finnish Japanese team at the Tohoku 60 centimeter telescope and observatory in Heraklion, where one copy of our instrument has been installed and currently used. So finally, we end up with this instrument. So if you see my pointer, so this is a schematic layout of our polarimeter. And this is a photo of Dipole 2 with the front cover removed. So we have polarization optics on top, and we have here a superchromatic half or quarter wave plate discretely rotated by high-end trinamic stepper motor. We use as an analyzer a plane parallel calcite. We have a set of those calcites with different thickness, provide beam separation in the focal plane from 1 to 1.8 millimeters. So depending on the telescope, we can put thicker or thinner calcite. So two dichroic color sensitive beam splitters, BV and R passbands, are installed just below the polarization unit. We use 3 CCD cameras, blue sensitive APG Alta and Santa Barbara ST402 for VNR passbands, and they all are connected and controlled via USB 2 interface, so the readout time for all 3 cameras is approximately 2 seconds. The polarimeter has a compact size and low weight, can be disassembled and taken with a handbag. It is controlled with a single industrial grade mini PCs equipped with 3 USB and 1 COM port. The USB is needed for camera control and COM port for stepper motor control. It is, as I said, optimized for remotely controlled observations. It can be mounted on the telescope and used without any service for many months. VNR registration channels can be simultaneously used for the telescope auto guiding if it's necessary. So detailed information can be found in the paper published by us in 2014 PAE conference series. So these are most important features of our polarimeter I want to point you to. First of all, as with any double image CCD polarimeter, 2 orthogonally polarized images are recorded simultaneously with the surrounding sky. So no errors due to variation in transparency in scene. A single measuring cycle normally consists of 16 rotation. So we use this full 360 degrees rotation measuring scheme. With this way, all possible rotation induced internal errors, which may arise, for example, due to dust particles on the retarder, are eliminated. And we use only standard calibration procedure with bias and dark subtraction plus flat fielding. And for calibration the images and reduced polarization, we use automated data reduction routines, which are based on the MaximGel software and VBS, Visual Basic Scripts. So 2 key ingredients which make our polarimeter effective for both domains. First of all, it's defocusing. So when we observe a bright star, we intentionally defocus the telescope, as this helps us to avoid saturation. We do it by spreading the image over the large pixel area. This also helps us to collect up to 10 to 7 photoelectrons per single image in ordinary and extraordinary light beam. This also helps us to avoid errors due to imperfect folding. The second key factor is that we use a plane parallel calcite. Instead of using more sophisticated Savart or Wollaston prism, we intentionally use plane parallel calcite because it split 2 orthogonally polarized light beams in parallel. So with such methods, we orthogonally polarized sky images are overlapped and overlaid over each of a dual stellar images. And because of that, the sky polarization is eliminated optically and automatically. So our polarimetry with dipole 2 is not affected by the sky polarization. And because of that, our dipole 2 is the instrument which accuracy is only photon limited. It can be up to 10 to minus 6 or a few parts per million, and a precision in the level 10 to minus 5, that is 0.001%, is routinely achieved on a 60 centimeter telescope. So this is a slide which I show you just to demonstrate this defocusing, because I very often asked how you do this. So this picture shows the image taken with the R-band camera, and the star, this double stellar image of a star, it is strongly defocused. So the separation provided by calcite is large enough to allow for this defocusing. So I'm not sure if it's well seen. So the total intensity inside this software aperture is 1.3 times 10 to 7, which is high. But the intensity, maximum intensity, and the pixels inside the diaphragm is only 12,000. So it's comfortably low, far from saturation limit. Of course, even with this approach, we still need to take 700 to 800 images to collect 10 to 10 photoelectrons. But because the image download time is only 2 seconds, it can be done in a reasonable amount of time. So the download overhead is not that long. And normally it requires 1 to 1.5 hour total integration time to measure polarization from sufficiently bright star with accuracy 10 to minus 5 in all 3 passbands. Of course, if we observe a faint star, we focus precisely and accurately. And in this case, the accuracy is limited only by signal to noise. So our dipole 2 polarimeter has been built in 3 copies. The first dipole has been commissioned in the end of October 2011 on the 60 centimeter KVA telescope in the La Palma. Later, it has been transferred to 1.2 meter telescope in Green Hill Observatory, Tasmania. The second copy, commissioned in April 2014, and 2.2 meter UH-88 telescope in Mauna Kea, has been used as a visitor instrument till the end of 2016. And the third copy, commissioned and installed starting from December 2014 on the 60 centimeter Tohoku telescope in Heraklion Observatory, Hawaii. So this is our workhouse, and we use it extensively up to now. And with the Tohoku 60 centimeter telescope, we can continuous observing runs starting typically from the mid of October and lasting till the end of June. And because the Hawaii is so conveniently located, literally on the side of a globe to Finland, we can do these observations in the daytime. The first dipole 2 was also used a couple of times as a visitor instrument for 4.2 meter WHD telescope in 2015, 2016. So it's a table below this slide, give you a polarimeter dipole 2 practical performance. So for their accuracy 10 to minus 5 and better, with a 60 centimeter telescope can be achieved with a star brighter than 6.5. And with a 2.2 meter telescope, the same accuracy can be achieved with the stars as faint as 8.5 and 4 meter type telescope. We can measure polarization with such precision for a star 9.5. So such accuracy is not reachable for photomultipliers, polarimeters. So they can observe polarization with few parts per million precision, but only for the very bright stars. For example, with the Anglo-Australian 3.9 telescope, HIPI polarimeter, I can measure polarization of stars with the brightness magnitude limit 6.5. For fainter stars, yes.
Under 5 minutes.
Okay, fine. I will be ready. Okay. We have been pretty happy with our Dipole 2 instrument, but a few years ago we decided to upgrade it. And so we built a new Dipole UF, Ultrafast polarimeter, which is basically a Dipole 2 on steroids. It used 3 high-performance Andor EM CCD cameras. This is a very nice CCD camera. It can be used in fast transfer mode because it has 2 image areas on the chip. One is for exposure and another one, masked one, for temporal image storage. So in fine transfer mode, the image download time can be very fast. And it's a very flexible system. It can be used with a conventional and electron multiplier. And the key dipole features are outlined below. So each camera is controlled with a separate mini PC. Even with a conventional amplifier, we have much faster image readout. And the polarization unit is made retractable. So if we want, we can convert our polarimeter, the normal photometer, with the fast readout. So up to 50 unbinded full frame images can be taken per second. So this polarimeter optimized for the use with a large telescope, and it was officially commissioned at the North in July 2019. Now, currently, it is available for the Nordic astronomical community as an instrument with limited access. And here is a link to this instrument with description. The first results obtained with the new polarimeter has been already published this year. And new, not yet published result will be presented to you in tomorrow's section by Yuri Poutanin. And with this instrument, we can observe with 2.2 meter Nordic optical telescope the star with a brightness range from, say, 3.5 stellar magnitude to 20.5 stellar magnitude. And the photo on the right side show you the Dipole UF mounted on the Cassegrain focus of the Nordic optical telescope. And 2 low images show the image of a stellar field with the polarimeter unit inserted in the optical pads. So all stellar images are doubled. And on the right side, the same field with the polarization unit retracted. Okay, so I'm done. Thank you for your attention.